Hello, welcome to this version of my video. In this version of our video, I'm going to be showing you two things. First, based on the new updates, if you're currently on the WipFrag 4.062, which is a new update released on the 22nd of April 2026. So if you're on this version, these are the new updates that is available on the new version. First, I like to talk about the color, the interface color. So you have three options for the interface color. So you have the white color, which is the mode I am right now. So you can see the brush up here to switch from one color to the other. So if you click the second time, you will be on this second color, which is basically designed for those who have a color blindness issue. So you have this color to actually make your interaction with the software easier. So if you switch click the third time, you have the black interface background, so that actually make work easier for people that like to work in this mode. So yeah, my best mode is always the white, and I like to work with the black mode also. So yeah, that's one of the updates that I like to share in this video today. Then the second update is pertaining SPFan. SPFan is a new fragmentation model. It's called the fragmentation energy fan principle. This model was developed by Joe Sanchidran and Finn Altolonin, and they published the latest version of the model in the just concluded 14th International Symposium of Rock Fragmentation by Blasting, that is the Frag Blast 14 in Turkey. So yeah, this model is currently being implemented in the software as a means of calibrating for the fine. So it's a fine target based kind of calibration compared to the existing calibration that is sieve based approach. So I'm going to be demonstrating that in this video shortly. So right now I'm going to be using this fragmentation image. As you can see, there is a lot of mid and quarks particle, and there is few of fine particle, but we believe there are fine particles under these blocks. So the application of calibration is to help you account for the unseen fine. So calibration focus on accounting for unseen fine. So there are fines that you can see, and you can resolve in this particular analysis. So you apply calibration. So applying the calibration for the fine target is divided into three categories. We have the medium, and the high fine target. So if you have a lot of fines in the fragmentation, that is in the blast, and they are visible, you can determine this by your visual inspection, and also checking if the end value of that particular analysis, I mean the uniformity index of the analysis, the end value is very low. If the end value is less than 1, so that means you have more than 30 percentage of the image area covered by fine. So depending on the level of fine you have in the particle, you can have a blast with a lot of fines, so you can visually view. If there is less fine, then you can use the legs, or the medium. Then if there is more fines, you can use the high. So I'm going to show you the interface of the calibration now. So this is the report. You can rename the analysis, and this is from mine 2 Northwest Bench Blast 231 image 1. So that's how I like to name my images, so it makes it easier, especially when you have more than 2 or 3 images. So let's proceed to the calibration. So you can see the calibration icon here. So just as it used to be in other version, is still there as the same thing in this new version. So when you click it, what changed in this version is that now we have no calibration. That is, what you see is what you get. So no calibration, that is, you are only interested in what you can see in the image. Then you want to calibrate, you don't have sieve results, then you can, based on the fine target, you can, from the visual looking of the blast, you can know, oh, there's a lot of fine. You use I. There is medium. I always recommend medium for most of the blast. Then the low, if there's few fines, so you can use the low. So any of these category that you select will help you account for the fines. And we, as I've said, the model was not developed by us. We only apply it to make it industrial, to make it industrially available for blasters to use, especially in situation whereby there is no sieve result for most of the blast. You can't sieve your blast. You can't sieve the whole mock pile. So if you can sieve the whole mock pile, then you can use the sieve target using the Kungstram, that is the Roxenramler model, and the Swebrek model. Those are very good for sieve target based kind of calibration, but you don't have sieve result. You don't have sieve results. The blast is huge. You can't sieve everything, but you can virtually you can see from the blast if there's a lot of fines, if there is less fine, and if there's moderate fines, and if there is a lot of fines. As I've said, also another approach by which I kind of make decision on the level of fine is using the end values, like the end value, and it's going to be very low, that is less than 1. If greater than 30 percentage of the pile, that is this image that you've captured, is having fine, so you can also use the n. So right now you want to apply the calibration. Let me just quickly go through the old kind of calibration we have, which is based on sieve. You have sieve results, especially with a slab or bed cut. So all you need to do is to click this and you enter the sieve values. You enter the sieve values here, and when you put the C value, you put the percentage passing. So then the software will recommend, you can say recommend, it's going to recommend the best kind of calibration that works based on the sieve that you have already input here. So you want to have the sieve result and you want to put those value here. Then you click the best. It's going to recommend the best based on the sieve results, and it's going to calibrate your data based on your sieve. But in this case, you don't have sieve result for blaster, so all you need to do is to select the fine. So based on the fine target, if there is low fine, you select low and you apply. That is, you apply the calibration. Then the software will calibrate the result and also show you what the calibration has done to your curve. One of the advantage of the SP fan is that it has less effect on the top sizes and give more focus to the calibration approach towards the tail, that is the fine area of the curve. So you can see the effect. So the software will show you the effect, how the software try to calibrate for the fines by lifting the tail. So you can see the tail is being lifted, and as I can also mention here that you can adjust the sieve that you have here. You can include more sieve to actually account for more fines. So depending on what you're looking for or what your target is, you can adjust the sieve, you can change the unit. So this is how to use SP fan calibration. As I've said, also depending on the fine targets. So for medium, I like using medium because most of the uniformity index will be between 2 or greater than 2 for most blasts, depending if you over crush the blast with a lot of powder. So as I've said, depending on the fine that you have in the pile, based on your virtual kind of assessment and based on the uniformity index assessment, you can select the fine based on medium, high, or low. So when you apply that, you have the results here. And I also like to mention that this is the SP fan equation, and you can see the parameters in case you want to use the mil value of the blast to include that value in your models. The software provides you with data to be able to understand how the model actually work and how the software is using the model. So you can see the function of the SP fan here and the parameters that actually calibrate this particular data, aligning it with your blast. So you can use these parameters also in your models if you want to understand more on how SP fan can help you improve your blast design. So once again, I like to mention that this SP fan model is not developed by us. So if you click here, you can see the paper and you can learn more about SP fan. The paper is included in the software, and the credit goes to the author. You can see the authors here, and you can read more on the SP fan equation and what the SP fan brings to the table when it comes to predicting fragmentation. And you can use now the SP fan on the WipFrag software and see what it brings to the table when it comes to calibrating for unseen finds. A lot of advantage and promising. So yeah, thank you very much, and let me know if you have any question.